Welcome to Oddly Real. I'm Nem Stefanovic. In the vastness of our universe, there is perhaps no object as mysterious as a black hole. A literal three-dimensional hole in the fabric of spacetime, such that anything, matter or energy, that enters can never return. It's an object that is made of curved spacetime itself. It's a boundary to the edge of the universe. The laws of nature conspire to ensure that we can never see into its interior unless we're willing to take a one-way trip inside ourselves. Even stranger still are the possibilities for what lies inside black holes, including an end to spacetime. In this episode, we'll describe the interesting details of black holes and how they behave. We'll also delve deep inside these strange objects into parts beyond our universe that even our greatest minds can't yet fully explain. The basic premise behind black holes is that when an object is compressed down under tremendous forces beyond a certain threshold, it will collapse in on itself with no way to stop it. The most fundamental way that we know this to occur is by the death of a large enough star after it has exhausted its nuclear fuel. The star must contain at least two solar masses, or 2 times the mass of our sun, to collapse into a black hole. There are no mechanisms in nature that would be able to counteract the crushing gravitational forces. In fact, a 2 solar mass black hole would be relatively small, since there are supermassive black holes that are found at the center of galaxies that can be billions of solar masses in size. On the opposite end of the scale, there are primordial black holes that range in sizes, even being smaller than atoms. These would be very rare and likely only created under the intense conditions and pressures of our young universe closely after the Big Bang. Of the few that could have been created, they would be slowly evaporating. Once these primordial black holes shrink down to the size of an atomic nucleus, they would still weigh on the order of 1 billion tons, but they would destroy themselves in an extremely powerful explosion. Their mass would be converted into energy that would be 1 trillion times more powerful than the most powerful nuclear detonations ever made on Earth. No new primordial black holes are being formed since there are natural degeneracy forces in matter that would resist it from being squeezed down into a form of a black hole. The exception being the creation of black holes from stars due to their tremendous gravitational forces, which overwhelm those degeneracy forces. Black holes themselves appear pitch black against any background light. They have well-defined sharp outer edges along their event horizon, which is a boundary layer that separates the rest of the universe from the interiors of the black holes. Just above the horizon, matter and energy can escape. Just below the horizon, nothing escapes, not even light. The mass of the black hole governs the size of its circumference. Under simplified conditions, it can be calculated as 18.5 kilometers times its solar mass. So a black hole that's 10 times the mass of our sun would have a circumference of 185 kilometers. Interestingly, black holes can also spin. For example, if the star from which the black hole was formed was spinning, then by the conservation of angular momentum, the resultant black hole will also spin. Depending on how fast it is spinning, the black hole will also exhibit a characteristic bulge along its equator, with well-defined north and south poles along its axis of rotation. A spinning black hole will also drag spacetime around with it as it rotates. This twisting of spacetime can be detected by looking at the twisting of gases as they fall into the hole. The rotation is fastest closer to the hole and slower away from it. In fact, black holes can also pulsate. Lastly, black holes can also have electric charges. In the event that there is excess charge within the black hole, either positive or negative, then electric fields will emanate radially outward from its surface. However, this condition doesn't last long, since a charge imbalance would attract the opposite charges in the surroundings into the black hole to neutralize the charge difference. Ultimately, just these 3 properties, mass, spin, and charge, govern the behavior of black holes as seen from their exterior, such as gravitational pull, its shape and size, and how it will deflect light around it. We should take a minute to realize how incredible this situation is. The fundamental properties of mass, spin, and charge are more the defining characteristics that you'd expect to see for subatomic particles, let alone a large-scale, incredibly massive object like a black hole. The tidal forces of black holes just above the event horizon can be powerful enough to tear a human body from head to toe while simultaneously crushing it from its sides. Tidal forces produce a vertical pull and a horizontal squeeze in gravitational fields. They occur around Earth as well, but they're much stronger around black holes. Paradoxically, the strength of tidal forces just above the event horizon of black holes decreases as black hole mass increases. This is because the horizon circumference grows proportionately with mass, but the tidal forces are proportional to the hole's mass divided by the cube of its circumference. Overall, the tidal forces near a supermassive black hole would be far less than that of one a few solar masses bigger than our sun. There's a region around the black hole from the circumference of the horizon out to 1.5 times the circumference where gravity is so strong that you can't orbit around the hole. The speed at which you'd have to maintain to prevent being pulled closer to the hole would have to exceed the speed of light, which is not possible. The only way to remain in this zone is to directly counteract the gravitational forces in a straight path away from the hole. Nature creates a veil, the event horizon, to block out any details of the interior of the black hole. They say black holes have no hair. This means that there are no clues that can be read from the outside of the black hole, like nothing sticking out from it, that would reveal any details about the star that formed it. For example, if the star had a magnetic field, it would have radiated away as electromagnetic waves when the black hole formed. If the star had a deformation, the bulges would have radiated off as gravitational waves. All that remains is the mass, spin, and electric charge, but no other details about the origins of the black hole. From the perspective of an outside observer, objects that fall toward the event horizon will be seen as falling slowly and then more rapidly as they descend. However, near the event horizon, they will appear to slow down drastically. When they reach the event horizon, they will appear to be completely frozen, never crossing through the horizon. Strangely, that is not what the observer would see who is falling into the black hole. They would see themselves crossing through the event horizon and continuing into the interior of the hole. This is a very extreme case of time dilation between two observers, and it is due to the effects of gravitational time dilation. In fact, if someone was watching a star of a few solar masses collapse to form a black hole, they would see the surface of the star start to collapse down. However, the surface of the star would also slow down and appear to freeze at the edge of the event horizon, appearing stopped to an outside observer. The entire process of collapsing a star with the circumference of our sun down into a black hole would happen within about an hour. But what happens in the interior of a black hole? This is where things get both weird and very interesting. There isn't a definitive answer, but there are predictions that are very well founded in physics. When you enter a black hole, you are removed from the universe. No matter or light will re-emerge from within, and no information can be sent out. There is a minuscule region of space at the center of the hole called a singularity, which contains the mass of the black hole in a space that is 100 billion times smaller than an atomic nucleus. The region from the singularity to the event horizon is nearly empty, with the exception of falling gases that were sucked into the hole, as well as the radiation that they're emitting from being superheated. If the hole was not spinning, it would be a perfect sphere with a singularity at the center. Near the singularity, the warping of space is tremendous. Space is so distorted there that normal Euclidean geometry can no longer be applied. The interior angles of a triangle would no longer add up to 180 degrees. They would be greater than 180 degrees. If you tried to compute the radius of the black hole from the singularity at its center to the event horizon, you could no longer use the formula that radius is equal to circumference divided by 2 pi. For example, within a fraction of a centimeter around the singularity, the radius of space could be millions of kilometers. Near the singularity, the spacetime in the region is very chaotic. Spacetime oscillates in a non-predictable pattern that will stretch and squeeze objects in various directions, which gets stronger and stronger the closer you get to the singularity. As materials fall in, there's a point where the tidal forces are infinitely strong and the oscillations become infinitely rapid. It is here, in these calculated infinities, that spacetime ceases to exist. Since nothing is truly infinite, this is where new rules exist that govern the behavior of reality, the laws of quantum gravity. Quantum gravity dominates physical reality at the point when objects become completely deformed in 10 to the power of minus 43 seconds or less. Beyond this, and spacetime no longer exists as a unification of both time and space. In fact, time itself vanishes, and there is no longer a way to say that something happens before something else. Space remains but takes on a different nature. It has no specific shape or curvature anymore. Instead, it's characterized probabilistically. It can take on any curvature or topology, and in each situation has a probability associated with it. It's not that space takes on a type of topology and switches to another, since there's no concept of time to make those transitions. This is very strange, and this condition is referred to as quantum foam. There tends to be general agreement that black holes contain singularities within them. But there are also other, less likely possibilities that can describe the interiors of black holes as well. For example, there is a solution to Einstein's equations that predicts, under some idealized conditions, that the star within the black hole will pinch off from our universe entirely. Specifically, a space-time bubble containing the star will separate on its own, like a little closed universe, away from our own universe. In order to separate like this, the closed universe would have to detach through a higher dimension of space in hyperspace. Ultimately, this closed universe could reattach itself to some other part of our universe or another universe entirely. The result would be a re-explosion of the star and even potentially a new Big Bang somewhere. Thanks again for watching this episode, and remember, oddly real, really interesting.